Hello and welcome to this week's review video. This week I'll be talking about a particular method in device scaling down, and that being strain engineering. Strain engineering was implemented in device fabrication in order to counteract a certain short channel effect. The short channel effect being velocity saturation. Now, velocity saturation is a short channel effect that causes mobility degradation on our devices. And when carrier's mobility plummets, our total current, our drain current also plummets. So you can see why strain engineering was implemented in our devices. Now, the gimmick behind strain engineering, the principle of it, in order to explain it, we have to go back to the energy band. And this is a EK diagram of our energy bands, the top being conduction and the bottom three being balance bands. The strain band, we modify the top conduction and also balance band to restore some certain mobility to our short channel devices. Now, strain engineering is a combined effort. We have to modify both bands, conduction and balance band. And first, modifying conduction band. This picture's better. There's a different, depending on a crystalline orientation, electrons travel much more easier. So, in conduction band, we strain engineer a easier route for electrons. You can see the red ones is known as two-folds, and so we split the conduction bands just like energy bands. We split to two new energy states and make the two-fold states much more lower, thus making electrons much more easier to go to our two-folds energy bands, two-folds conduction bands. And what about the balance band? The balance band, we make our balance band more steep or more curvy in order to achieve a lighter effective mass, thus restoring mobility. Now the final question is, how do we augment the bands? Well, there's two methods. There's a global strain and local strain. I'll explain the local strain because it's more accepted in the field and much more easier to implement. So the first local strain, we used a certain edge stuff known as sizzle, and sizzle will provide enough stress for the device in order much needed to strain the device. So as you can see the picture right here, if we implement the compressive sizzle to our P MOSFET, it becomes a compressive stress. On the counterpart, the NMOS device, the stress becomes more tensile. Now the final method is a stress memorization technique, and this one, on our fairly finished device, we just give damage to our source drains and just don't bother because the cracks between the amorphized layer will just create a natural stress onto the device, thus achieving a strain engineering. Thank you for listening. This has been Myung Kim.